So,
Meeting is
and,
being recorded.
and so I don't need to do it. If you guys want to do something else, I can hold this off. It's just something I put together, and I don't care whatsoever if I do it next week or not. So, Peter, you can decide how you want to move this
I,
forward.
I think it would be great if you could do it next week.
Oh, okay.
It's a good change of pace.
The,
I
the,
can,
there is an
yeah,
agenda for those,
I could use
just
it if they have it.
for people who want to
I
know
looked
what's
for it
coming up.
yesterday, they didn't have it. Zero.
Okay, everybody can see my opening slide.
Yep.
Good.
Okay. Um, so this is the first, like I said, about 3/4 of what the GR class is going to be about. And it's going to be differential geometry. And so theoretical physics, what it's about is taking our concepts about the real world into rigorous mathematical form. And sorry, that's for better or for worse, but that's what we do, and we're going to have to deal with the mathematics. Theoretical physics doesn't do that for its own sake. It does so to fully explore the implications of what our concepts about the real world are. So, to a certain extent, the spirit of theoretical physics can be cast into the words of Wittgenstein, who said, "What we cannot speak about clearly, that we must pass on in silence." So, if we have concepts about the real world and it's not possible to cast them into precise mathematical form, that's usually an indicator that some aspects of these concepts have not been well understood. Everybody follow that? Any questions? So, if physics aims at casting these concepts into a mathematical language, then you've got to understand that mathematics is just that. It's just a language. If you want to extract physical conclusions from this formulation, you must interpret the language. That's not the purpose or task of mathematics. That's the task of physicists. And this is where it gets difficult. Mathematics is just a language, and about that language, Wittgenstein also said, the theorems of mathematics all say the same, namely nothing. Okay. Does everybody know what Wittgenstein meant when he said this?
Isn't he just reformulating the earlier view that mathematics is moving around symbols,
Well,
and that
that's certainly a lot of it. Yes. Okay, good. So what does he mean from the point of view of a physicist? Obviously, he doesn't mean that maths is useless. He refers to the fact that if you have a theorem of the form A, if and only if B, A and B being propositions, then obviously B says nothing else than A does. Although also A says nothing else than B does. It's a tautology. So logically, it's a tautology. Psychologically, and for understanding of A, it might be very useful to have a reformulation of A in terms of B. And that's the kind of thing that you do as a physicist. This is what understanding mathematics is about. You have this language, and for the idea of this course, we're going to provide proper language for differential geometry. Any questions? So we'll develop mathematics from a higher point of view. We're going to assume that you have some prior knowledge about physics subjects. So far, you have certainly used a fair amount of analysis in order to study things like electromagnetism and quantum mechanics and stuff like that. You've used a lot of algebra, mainly linear algebra, and we also did a nonlinear dynamics course, so nonlinear algebra was available as part of that. And we've used geometry in a lot of different ways, and probably very often in classical mechanics. So you'd appeal geometric intuition, sorry, in setting up your problems or finding the solution of a problem. So these are the three major tools that we're going to use for differential geometry: analysis, algebra, and geometry. Now, quantum theory lies primarily in the intersection of analysis and algebra, and it's usually called functional analysis. Whoops, I don't think I did that properly. Is that below? Where? No. All right. So here we go. Quantum theory is in the intersection of analysis and algebra. So when you look at algebra and geometry, that's the primary tools of statistical physics. I'm sorry, I don't know why. Must have been auto completed something else. So to do statistical physics. Okay. So, as I said, the intersection of geometry and algebra is primarily where statistical physics lives.
I have a question.
Okay.
Why is geometry not included in quantum theory? I mean, quantum theory tells us we don't know exactly where a particle might be. We talk about momentum, and all that concept requires geometry.
Well, if you actually go into the mathematics of it, it doesn't use geometry. If you are careful about how you do quantum theory, you'll find that geometry plays very little role. You have to be very precise about what we're talking about. So if you want, I can talk more about that, but there are this is part of the interpretation but you have no trajectories in quantum theory. There's no, you know nothing about what particles do until they're measured. So geometry, the way classical mechanics works, is completely foreign to geometry. Clear?
Okay.
Okay. So the intersection of analysis and geometry is primarily what classical mechanics and electromagnetism uses. So now we've got the three major tools, the places in which we use these, but the last one, the middle, that's what we need to do in order to do general relativity. So in the middle of this intersection is where differential geometry as a mathematical subject lives, and it's differential geometry and general relativity that this course is mainly about. So the mathematics of this course will be part of the mathematics of all these different theoretical subjects and where these three fields intersect. That's the rough idea of this course, a very rough idea of this course. Now, we're going to discuss the rest of this class about the more detailed structure of this course and the development of differential geometry. So we're going to start, and we're going to start with sets. So we'll talk about set theory because in any space in classical mechanics, the space of configurations or the phase space, in electromagnetism, the physical space you work in, quantum mechanics, there is a space, but it's not the physical space. It's your Hilbert space, which is configuration space. So if you have 10 particles, the dimension of your Hilbert space is 30 dimensions, not 3 or 4. And but all of it, including Hilbert space, has to be described in terms of set theory. So all of the spaces we deal with are currently sets of points, and that's the coarsest structure of a space, whatever space we're dealing with. It's a set, but what precisely is a set? Well, usually one deludes oneself into thinking that you understand what a set is by saying a set is a collection of elements, but that just raises the question, and again, this damn autocomplete just raises the question, what's a collection? And what are elements? So we certainly need to do better. There's a fundamental problem. If we start writing a book about mathematics and all of the pages are empty, what could be the first definition that you would place in that book? For a definition, you need notions that you already have in order to define a new notion. That's the structure of mathematics. You build from the bottom up, and you keep a collection of lemmas and theorems and all of that stuff. And then you start building new axioms from all the things that you know are true, and you continue building this great edifice. But if you don't have any notions yet, how do you start? Well, what Hilbert showed, others prior, but Hilbert had played the biggest part in axiomatically creating all of the various kinds of structures. So we'll have to write down an axiomatic set theory. But that then raises the question, well, how do you use the language to write down the axioms of set theory? So what we are going to do is starting with logic. We need this other building block. So we're going to use that starting point as logic. We'll deal with propositional and predicate logic first. And using that, I'll define our language, and then we'll be able to write down the axioms of set theory. So that's what we're going to start in 2 weeks. We're going to start on logic. Once we can have logic, then we can build the axioms of set theory, and we'll take our sets, and the question is, what can you do with them? One thing we certainly need in at least the 4 subjects that we primarily usually work in, classical mechanics, electromagnetism, quantum theory, and general relativity, and subset of that is special relativity. We need a notion of continuity. So, for instance, in classical mechanics, particles don't jump. The particle trajectory doesn't stop somewhere and start somewhere else again. It's continued from every point to every point. This is usually known as
Newtonian.
No.
How about when one particle scatters off another particle? Don't their trajectories discontinuously change?
No, they're continuously changed.
Or hard sphere scattering.
It does not ever stop at one place, and a light year away, it starts up again. It's going to be continuous. It may not be differentiable, but it's continuous. Understand? Clear?
No, I'm thinking about the vector describing the propagation of a particle. Hard sphere scattering off another particle, that vector does change discontinuously.
Yeah, but that's a derivative. I said it may not be differentiable, but it is continuous.
Okay, I don't want to argue the point. Go ahead.
No, I want you to understand what we're talking about. When you've got 2 particles and they intersect.
Oh, okay, their trajectories, their positions are continuous. Their velocities are not.
But I said it may not be differentiable.
Okay, okay.
I
We're-
only am talking about continuity, not differentiability.
The center of mass moves continuously.
Sorry?
The center of mass of those colliding particles moves continuously.
Yeah, but I'm just saying that's why we need to understand what continuity means. Because you can't have a particle stop somewhere and somewhere else start again. It's got to be very close. Okay. So you need a notion of continuity. And we're going to use various kinds of distinguishing certain subsets of the basic set that you're dealing with in the space you're dealing with. And that leads to the notion of topology. So we're going to go from logic to set theory to topology. So we'll deal with topological spaces and all the notions associated with that. Now there's an abundance of topological spaces, such an abundance that you can't even classify them. So we're going to need to restrict somewhat to what I consider to be interesting topological spaces from the point of view of a physicist. Now, mathematicians, topologists may disagree that the only ones I'm going to write down are the interesting ones. But I think from the point of view of theoretical physics, the immediately interesting ones are the topological manifolds. And that's what we're going to work with. So, topological manifolds. We're going to define a topological space that locally, in a very small region around that space, the point looks like some d-dimensional Euclidean space, r to the d. That's what a topological, this is, we haven't gotten to the point of to really understand that, but for many of the things that you've looked at in the past, this should make some sense to you. Any questions? Anybody not understand what I'm talking about? But that's not enough. If you have a topological manifold, you also need in physics, especially in classical physics, a notion of the derivative. So you need to be able to talk about the velocity of a curve. And that can't be done in topological manifolds. So we're going to develop the idea of differentiable manifolds, which are a subset, a definitely a subset of topological manifolds. So we're going to start logic in 2 weeks, and after we finish that, we'll do set theory, then topology, topological manifolds, and differentiable manifolds. And
Why do
different, yes?
Why do you feel that you have to spend time on set theory and logic rather than just plunging in to topology? Is it that you don't feel that you can properly characterize topology without going through set theory and logic first?
No, you can't. Not if you're going to be precise. And the point of this course is going to make you understand precisely how all of this works together. So if you want precision, if you want to be able to understand what you're talking about, you need to start with logic. All right, differentiable manifolds are an entirely new beast.
Are those numbers besides each category represent years?
I hope not. They're the tower of what we're working for. Number one is differential geometry. All of the other things are the basis of it. So you start from the bottom and work your way up the tower.
No, I understand all that. I'm just thinking about covering all that stuff once every 2 weeks.
Yeah, well, might take
Yeah.
us 2 years. Who knows?
Okay.
All
We're
right.
all in.
Yeah. Well, I'm 81. I don't know about the rest of you. So I haven't got that much time left, especially given my family history. This is irrelevant, so I'll just go on. So, in order to understand differential manifolds, we'll need to introduce the technology of charts. And the technology of charts will be the first time that we make contact to much of the rest of this formalism. They're used almost in all of standard physics course, all of classical mechanics, electromagnetism, quantum theory, and general relativity are formulated in charts. So we're going to spend a fair amount of time talking about charts. So we'll talk about it considerably further on in the course, but and we'll do a technical idea of what a chart is. But just so you can think about it, a chart is like what a sailor uses, a chart of the world. If you want to travel around the globe and you want to know where you are and where you want to be, you take out an atlas, and in the atlas, you turn to the pages and you find the appropriate chart around the point where you are in the real world. Then you can navigate in the chart here and there, and the chart should be a one-to-one picture of the world locally. This is a small region around the Earth. And because you have be able to move in the world using that kind of a chart, at some point, it's a very small region, so you would have to leave the page when you move to one of the edges. So if you're gonna go through the edge, you better turn the page in the chart and find the other page that slightly overlaps the one that you're looking at with the one that is going in the direction that you're going in the to find the chart you need in the atlas.
Charts sound like geometry.
It's a basis of part of it, yes. We're heading towards differential geometry, which differential geometry is obviously geometry, a subset of it. So here's looking at the Keys in Florida. So if you're going down the Keys, you're in this chart and you are going to go run out here. You have to find the next page, which is down here, and the two of them overlap. And then you continue moving along here. When you're going to go past this overlaps this chart, and you continue moving along here. So everybody understand how charts work roughly? This is not precise. Okay. So you can navigate from one chart to another chart. Very much the same thing. You're looking for another chart that overlaps and understand how the overlap works. And that's the whole philosophy behind manifolds, and certainly behind differentiable manifolds. This is the big insight that Riemann found in developing differential geometry. So differentiation on the charts, each chart is a part of R to the D. In the picture we're looking at right now, that's R2, for instance. So once you can understand differentiation in the charts, then we'll lift that notion of differentiation, and we'll talk about lifting as well. And we'll lift the general concept of differentiation from Euclidean spaces to the surface of the manifold. So that's one of the key things that we need to understand in differential geometry. But that's the entire philosophy. It's roughly the idea of the chart, except for the technical terms. And we'll come to that later. Okay, once we've gotten that, we're going to have to get another one, which is very important, but almost never talked about in physics. At least I never found about bundles in most physics general relativity classes. Once we have differential manifolds, we'll come to a notion which is yet another structure, and it's called bundles. Now, the idea of bundles, if you take a manifold and you take another manifold, and to each point of a given manifold, you attach the other manifold or one of a set of manifolds, then so you can attach another space to every point in the surface of the manifold, and you build what's called a bundle. Could be a vector bundle, could be another type of bundle. Usually we attach the tangent space and use that at every point of the manifold. Bundles are a very important concept in geometry, in differential geometry, and indeed much of modern physics can be understood and cast into the language of bundles. But I've only found it usually by mathematicians as opposed to physicists. By the way, it also works for particle physics and gravity, etc., and certainly for quantum mechanics. So that's going to be an important topic. Now, just to let you realize, we often talk about the notion of a position vector, and there is no such thing as a position vector. No matter how many times it's been said, there is no such notion. Now, in bundles, you can learn there's also no such thing as a wave function in quantum mechanics. So we're going to eventually be able to understand why the notion of a position vector, you can use it, we often do, but if you look at it closely, precisely, then it all goes away. It fails. The same thing is true for Hilbert spaces in quantum mechanics. You can get away with the notion of a wave function, but if you look at it closely, it fails. So a position vector is just a collection of coordinates, but they do not constitute a vector. And the wave function is in quantum mechanics is not a function at all. It's a section in a complex line bundle over the physical space. You won't understand this now, but hopefully by the end of the course, you will. So these notions are all needed if you really want to be able to precisely describe what's going on. I'll give a simple example of a bundle. A trivial, I was going to do I only did the trivial bundle. I didn't get around to, I couldn't finish the non-trivial one. I was working on it when you all came in. So we're just going to stop at the trivial bundle in the Appendix A at the end of this lecture. Okay, so we're going to start with logic. When I move up to set theory, topology, topological manifolds, differentiable manifolds, and bundles. And finally, we'll arrive to what we need to have as the tools to understand general relativity. So there's various ways in which you can talk about bundles. The way physicists usually talk about it is in terms of connections instead of bundles. So if you do that precisely, it turns out they're equivalent. The two are isomorphic. So I'm going to talk about the terms of bundles, but this is the same idea as a connection in differential manifolds. So this, at the end, we're going to deal with tensor fields and all of the substructures previously. So we're going to get geometry, symplectic geometry, metrics, all of the stuff necessary to understand differential geometry. So a differential geometry could be a symplectic geometry, could be, I don't know what the hell I wrote here, but that's obviously another might be phase space, I don't know. Anyway, the idea of differential geometry is a much bigger subject. For virtually all the dynamic systems that were going to be of interest to us, the phase space is equipped with a symplectic geometry. So that's going to be an important idea we're going to work with. And there may also be a metric geometry, and that's certainly the case in electromagnetism and the special relativity and general relativity. But for those, in addition to symplectic geometry, you need a Lorentzian metric. And this is a structure, another structure that sits on top of everything. So in order to deal with all of these ideas professionally, you're going to need to understand more or less all of the things that I've described. And we're going to start in 2 weeks. Yeah,
Could geometry just be a modified geometry? You start. It looks like if you replace geometry every time you said geometry, it makes sense.
no, I don't, it might have been, I don't know what the hell I was speaking to the.
Yeah, that's what I'm saying. It sounds like it interpreted geometry as geometry.
That might be it.
That was
So
my interpretation of geometry.
let me see if that makes sense if I go in here. Yeah, okay. So,
And on the top line too.
yeah, yeah. Okay, I think that's what happened. Okay. Where's it? Up there it is. Okay. Yeah. Okay. Thank you. Yeah, when I was making these up, I was using I was saying things as I was talking and then went back and changed things like it got never gets the punctuation right. So I do all that and I missed that there. But thank you. Yes, that's what it's about. So you'll learn all of these ideas and it's physical mathematics. Up to here, we've used physics such as classical mechanics, electromagnetism, all of this stuff. And all of those physics courses can be, or areas, can be understood, properly understood by mastering all the mathematics we're going to cover. So the purpose of the course is to develop these mathematics and to show mainly by examples how the insights you gain here play out at the level of physics. So that's the idea of what this course is going to be like. All right, we're going to move on to bundles, a trivial bundle only. So the electromagnetic field is a U1 fiber bundle. That's what the field actually is. U1 is a symmetry. You should know it in quantum mechanics. It's the circle, symmetry of the circle. And we're going to get a really rough intuition of fiber bundles to get a basic feeling and the visualization of some of these things.
Thank you very much. I will do it.
Okay. I also want to show how we actually describe a simple fiber bundle. So we're talking about spaces in mathematics. And by the way, all of this is going to be really, really rough. This is not going to be accurate. We'll get to it when we get to bundles, but I just wanted to give you an idea that you could get a rough idea of what it's all about. So you can think about spaces. Probably the simplest space, not the real simplest point space, but continuous space is R1, the real line, which goes from minus infinity to plus infinity. And usually we use these open parentheses to mean that they're open sets that you can never find infinity. But in functional analysis and in complex analysis, you can append infinity and consistently make it a closed set. That is, you can actually reach to infinity. So we'll talk about that later. That's a whole thing that we talked about it when we did complex analysis and we did the Riemann sphere. At one of the points at the Riemann sphere, that was the location of infinity. If you remember back then, that must be 3 or 4 years ago. But anyway, it has all of the numbers in between 0, 1, and everything in between, as well as the big integers, small integers, all of the numbers. And if you count the number of points between 0 and 1, you find that that's the same as the number in all of the real line, which is also the same as the number of points on the plane, and in R3, and actually any Rn where n is a finite integer. So you can count the number of points, and all of these different things are the same. So the thing that's nice about R1 is that it's a space we understand. At least we think we do. I'm going to treat it intuitively because we know that there are points in the space and how close things are to each other. So that allows us, using those ideas, to talk about it intuitively rather than precisely. And we can even measure how far things from each point is. You take the difference of the two numbers. So we have a natural set of coordinates on this space, and that set of coordinates is literally each number in the real line. So we can assign a coordinate system to this space, and we don't have to, because the numbers sort of represent points intuitively without the coordinate system, but it's the best example I can think of. So the next best example is what's called R2, the plane, the Cartesian plane. We're dealing with Euclidean structures here. All right, there's many.
Let me ask one thing, Bob. When you're talking about the number of points on R1, that's not countable. That's a different type of infinity from the countable infinity, like the number of numbers.
Well,
That's
it's
countable.
It's Aleph
Aleph sub
1.
1, isn't it? Yeah, Aleph sub 1. That's what I wanted to ask. Because Aleph
That's the
sub
number.
null is
That's the cardinality. That's what cardinality means, is the number.
right. Okay, so it's Aleph sub 1 is the type of infinity you would refer
Right.
to. Is that
Aleph
right?
0 is the integers or the
Countable
real
infinity.
number, the natural
Yeah.
numbers, all of those things.
Right. Okay.
the even numbers, all of those things.
Right. The countable infinity, I think.
Right. But the cardinality means number. So it is
Okay.
a description of counting the number of points. And you can do that using Cantor's description of infinities, and the number of points that are countable are Aleph 0, and the number that are uncountable. It's a poor language. It's an English language issue, not a mathematical one. You can count them, and the number is Aleph 1.
Also, one a mathematical friend of mine uh, told me there's also an Aleph sub 2, which is the number of possible functions.
Right.
Is that true?
Yeah,
Is that so?
that's true.
Interesting. Thank you.
Yeah, not a problem. So here's an orthogonal coordinate set for not all of R2, but a small subset of R2. And the idea is that you can choose every point in the plane. And the way we usually do it is and that's the Descartes' idea. And we usually think about around coordinates in terms of orthogonal coordinate systems, but that's not at all necessary. And when you think about it in special relativity, you should realize that it's usually not orthogonal. So the Cartesian plane, R2, is just a pair of real numbers. And you could use a symbol X to be one real number and another real number to be Y. So in topology, you don't need coordinates. Plane exists just by itself. But as you move up the hierarchy we're talking about here, you need eventually you don't need it, but it is usually fairly easier to think about things in terms of coordinate systems. So coordinates on the plane are different from coordinates in the line. Coordinates in the line are pretty straightforward. They're just an assignment of a number to a particular coordinate. But in the plane, we can pick different angles. So if we saw the previous one where it was orthogonal, but I can tilt that coordinate. And then if we're moving in the plane, we're going to be traveling a different amount of X and a different amount of Y than you do in orthogonal ones. So the angles between R2 do not need to be orthogonal. This is a perfectly good coordinate system. Every point in the plane is just sorry. Okay. So this is a perfectly reasonable coordinate system. And it is not able to change the coordinate system in the real line, but for r to the d, r to the 2, where d is greater than or equal to 2, you have to choose how you're going to distribute points in play. So connecting the points in here depends on the coordinate system. But you can map every point in the plane to a point in the real line. That's why they have the same number of points. Okay, let's move on to spheres. This is a little bit independent, but we're going to talk about coordinates a little bit later in the course. But for the Cartesian plane, it's our next most natural space, R2. As I said, you can have R to the D, and you can keep going up as many as you want. They have all the same number of points as the real line, so you can always map everything from any plane in RD to the real line. Okay. So let's talk about a different kind of space. Instead of R to the N. R to the N are whatever. They're infinitely big and there's no boundaries, at least unless you go into functional analysis or complex analysis where you can append infinity. Okay. There are things like spheres that do have boundaries and don't contain, that's not accurate, I'm sorry. They do contain all the numbers. You can count them, but they're a subset of R2, even though the same number of points on the sphere is the same as on the line. Sorry, I wrote that wrong. I don't know what I was thinking of at the time. So we can notate spheres just as we did with R to the D. We can write them as S to the N, where N is the dimension of the sphere. So we can do the very simplest one, S1, and that's just a circle.
No, it's a 3D object.
Okay. I'm sorry, question? Okay. So we're going to need to describe a circle a little bit more. So you can draw a picture of a circle rather simply, but you have to be careful because when I say a circle, I mean a one-dimensional object. The circle is simply described by a single coordinate like theta. So you go around the circle, I increase theta between 0 and 2 pi, and eventually it comes back to the same place that it was. And you can keep going, but you're just going around the circle and around the circle and around the circle. So you can sometimes just use the interval from 0 to 2 pi to describe the circle. So this is a perfectly fine circle, this line. So that's what it means to be a circle. It's a little tricky around circles. We can describe them algebraically and using tomology, but you can just use a line. Okay. So,
I have a question, Bob.
yeah,
When you look at that diagram, you see the point at 0 and the point at 2 pi. Those are the same point, but yet
well,
they're
one of
separated.
them should be open. I'm sorry, this is actually, that was a mistype.
I'm looking at the diagram. I'm not
Yeah,
looking at that.
but the thing is, you can get as arbitrarily close to what the hell? I'll have to change this later. Annoys me. Ah, that's what the problem is. Okay.
I'm looking at the diagram
Yeah, but
in the box.
you have to think about this as being an open on this side. So you can get as close to 2 pi as you can. You can get arbitrarily close to 2 pi, but you don't reach it. It's a half open interval. It's not a closed interval.
Bob,
That and in that case, then you don't run into the problem you just talked about. That's why you need to think about open and closed sets, and we'll talk about that when we get to set theory.
Bob,
Yeah,
this doesn't in any way then define the uh, diameter radius of the circle. It's only in terms of the angular position on the circle.
right.
So this is a circle of any size.
No, this is a circle of size
Well, but I'm
one.
saying, but in our
This
context,
line goes from the
right?
if you had the proper way to do it, which I did only for a unit circle, is to take the perimeter as uh, the piece lining up the line. So this should go from 0 to the length of the perimeter. That's the proper way I was being sloppy here. I apologize.
So it's
Well,
not
what would
defined
be
in terms of
different?
the angular position.
Yeah, well, that's what I'm saying. I should have said instead of using an angular position, which is the way I
Oh, I
usually
got it.
think about
Okay,
it for a unit circle,
right.
but um, you should actually use it to be the perimeter.
Got it. Got it. Thank you.
Yeah, sorry. Can I? Okay. Okay. So,
Oh, I forgot.
yeah. All right. So, but the way in which we usually think about it is in embedding it into a uh, space of a higher dimension, usually almost always a Euclidean um, space. And so for S1, we'd embed it in R2. So uh, the easiest way to think about the circle in terms of an angle is to we're doing a unit circle again. I always think in terms of the unit circle. I should be more precise, but I was sloppy. All right. So you can just choose a point in C2, actually C, not C1, not C2. Yeah. Okay. So you can write this the the circle in C1. It's just the exponential of I to some initial point theta 0 plus theta, and you take in R2, you take the real part and the imaginary part, and that would be a circle. So here I chose an arbitrary point pi over 3. So that's your initial point on here. And then you go around as theta goes around. And again, I should be doing this in terms of the perimeter, but I'm doing it in terms of the angle. Okay. And if you do it with a plus here, you go around clockwise, counterclockwise. And if you use a minus, you go around clockwise. Okay. There are, of course, higher dimensional ones. We'll do S2, obviously, that's a sphere, an actual sphere, but it's only a surface of a sphere. We think of objects in 3 space, but we're not dealing with a sphere embedded in a higher space. We're talking about a 2-dimensional surface. So it's like the surface of the Earth. We describe the surface of the Earth using 2 coordinates, latitude and longitude, which means it's only a 2-dimensional space. So S2 is usually called the 2 sphere. S1 is sometimes called the 1 sphere. So if you're going to use it embedded in another space, you need to have an additional coordinate from the size of the sphere. So for a 1 sphere, you need to embed it in R2, and from S2, you need to embed it in R3, and you can do coordinates. So if you were doing a 2-dimensional sphere, and you wanted to get the embedded, you would have x squared plus y squared plus z squared equals 1, and all of the set of coordinates in R3 that describe this are a 2 sphere. Now, there's a couple of different ways that you could take a sphere, a 2-dimensional sphere, and embed it in R3. The one we usually do is using the points x squared plus y squared plus z squared equals 1. But you can do it directly in, well, you can solve that for z of x and y, and that will give you a way to describe the 3 space. The other way you can do it is to do projective geometry, which I'm not going to talk about right here. What is going on? I got a beach ball. I got no idea why this is happening. Looks like it's time to take a break.
Okay, so break for a few minutes here.
Yeah, take a break while I try to figure out what the hell's going on.
How much more time do you have, Bob?
I guess 10, maybe 20 minutes.
Okay, just checking. I'll be right back.
Yeah.
But I'm saying that they're to the next round, are they not? Oh, I get, okay, maybe it was some Argentina.
I mean, it's amazing.
Did he score any goals?
Yeah.
Well, so they scored in the last.
They scored 3 goals in 12 minutes. They scored 2 goals in 3 minutes. Tied, and then in the extra time, they ended up scoring the game. I don't think each couldn't quite believe it. They thought they had it, and they thought they had it, and then they wouldn't have it.
So they had 2-0 and they lose 3-2. Well, you could, you're not gonna.
I could hear screaming. Are you okay?
Yeah, just.
I should.
Yeah, just go. We appreciate that. It didn't roll up to that at all.
They move things around. I can't pause the recording. Sorry. Yay.
I don't know if anybody out there is watching the World Cup, but apparently Egypt was ahead of Argentina 2-0 with like 12 minutes left in the match, and Argentina scored 3 goals in the last 12 minutes or something to win.
Wow.
Yeah. Yeah. My wife's a big soccer fan, and she was watching it. As it turns out, in the unit right below us is a guy who was born in Argentina. His parents were like diplomats. He was raised in a bunch of different places, but I could hear him screaming all the way up here.
Wow.
Yeah,
Okay. So I finally,
you figured it out.
well, I don't know that what I did was I stopped the presentation, and that seemed to have finally done it, but I had to get out of the share and get back into the share. Okay.
Well, this is really good stuff for someone who's never had anything like this. I'm enjoying it.
Okay. Okay. So is everybody back? I don't have my Zoom thing up.
I see a couple empty chairs. There's still Husky and Shulman and Peter. Yeah, there are a bunch of empty chairs.
Okay. All right. Come on, Peter. come back. Richard, come back.
What did you say?
Well, I'm going to can everybody see the slide?
Yep.
Okay, now why can't I see them? This annoys me no end. All right. I'm going to stop the share and go back because I can't seem to find out how to get to it. All right, now I can see it. Sorry. So we talked about a second kind of space, the spheres, as opposed to the real line or S to the N, R to the N. And you have to realize there's a difference between the two. They're different kinds of spaces. Real line is infinite, non-compact, and non-boundary, unless you go into complex analysis. These spheres don't have boundaries, so you need to be careful about that. So there's no boundary on S1, there's no boundary on S2. They're compact, meaning that they don't go out to infinity unless you can go into functional analysis or complex analysis and end with infinity by mapping it to the Riemann sphere, for instance. But they don't have any place where you run into a wall that you can't go further. Even in the line, the one side is open, one side is closed, but the other side is open. So you can get as close as you want to 2 pi, but you can't ever reach it. There's no wall there. So the same thing is true in S3. But S2 is not any kind of Cartesian product. It's not a simple splitting into 2 spaces. So let's talk about, finally, let's talk about a trivial fiber bundle. Okay, so we're going to use some new kind of spaces using Cartesian product. So as I said, we're only going to do the trivial bundle. So we're going to do the Cartesian product between R1 product S1. So what does this collection of symbols actually mean? Well, it's, you can take any point in R1 and append to it a copy of S1. And I'm going to try and show you how that works. And here's my, let's see if we got the image up here. Yeah. Okay. So here's R1 going off to infinity. And that's why it's dashed. And at the point I'm at here at, it looks like, I guess, 4, I append a circle. So I've got this is infinitely thin, not thick the way it's drawn. And this is infinitely thin. So that's, we're going to do that. Then we're going to collect another point and add another circle. And we're going to keep doing that. So as you keep adding more and more circles, you'll eventually realize that this is just a infinitely long cylinder. Okay, so that is the Cartesian product of R1 with a circle. Okay, everybody clear about that?
Is the center of the circle? It's not along the center of the circle. It actually touches.
Yeah, it has to touch. It has to touch the R1.
It has to touch
you literally have to have some point on the circle at the point of R1.
Okay.
So if you think about it, you've got a coordinate system, a point in R1, and then the circle is the second. So I could have used, instead of a circle, I'm doing in an embedded space here. I could have done it in a 2 space simply by having a line and a line going out as a different way to do it. But I think this is a little bit more intuitive about what we're doing. And when you go to non-trivial bundles, it becomes important to thinking about it in terms of the embedded space, at least for me.
Bob, I don't understand why you actually get that cylinder. Shouldn't if the points
Because
of
every
contact,
point in R1 has a circle on it. I've done this only every few parts of R1.
but couldn't those circles be spread out around that line of contact going down?
Yeah, this should, as I said, it should be a cylinder.
I guess I don't quite understand that drawing. I would
Well,
think that
if you've got it embedded in R3, you've got a line, every point on R1, every single point infinitesimally far away from this circle is another circle. And then infinitesimally close to that is another circle. So they're continuous. Therefore, it's a
boggling my
cylinder.
mind. Okay, I really have to think about that one.
Well, think about continuity on the real line.
I am.
Okay, at every point, every aleph 2 points, you've got a circle. So infinitesimally close to a circle here is another circle. And then infinitesimally close to that one is another circle. So in order to build the full thing, you have to do it at cardinality.
Every point.
Every point has a circle on it. So, and that's continuous. So the circle has to be continuous. That's why it's a cylinder. Clear? If
Okay.
R1 is continuous, the circles have to be continuous. They have to all match each other because they're infinitesimally close.
Okay, they have to match each other. It's the infinitesimally close. I think that I wasn't quite following.
Well, you understand how we do differentiation, right? You
Oh,
do the
yeah.
limit as the distance between them goes to zero. The same thing
Okay.
happens here. The circles get infinitesimally close. The limit as the circle goes, as the distance between the circles goes to zero, but never quite reaches. That's what continuity is about. Understand it now?
Okay. Okay. I still have to think about, to me, let's take, I look at that as a spring.
That's not the
And
way it works. This one goes right up infinitesimally close to this one. The second one gets infinitesimally close to the first one. It is that I had to, in order to do an animation, I had to use a finite number of points. I don't have an infinite number of points that I can show you circles for. So this is only a finite subset of the
the fact that they have to be infinitely close is kind of like a glue that coats them all together. It's kind of, but
that's continuity. That's what
I guess
continuity is all about. So,
why is it a right cylinder? Why isn't it sort of skewed around that original line of contact?
well, you never see the line. The
Right.
line is part of the cylinder. So, however you angle this, it's still a cylinder. That's I happen to have used an
Okay.
orthogonal
Okay.
coordinate system. So,
All right. I think I you're just defining it that way in the space. I can't think of it as a physical spring or
no, it's not. It
okay.
is infinitesimally close. The second point is
Got it.
infinitesimally close. The third one is infinitesimally close. You'd never be able to tell the difference between the first one and the second one.
Okay.
It's the limit as the distance between the two of them goes to zero.
Right. Okay. That's not a problem there. Okay.
Okay.
I don't want to hold this up.
So everywhere over R1, we get a little circle. And since R1 is continuous, so will the circles. And you'd actually get an infinite cylinder if you did it carefully at every single point in R1 because it's continuous. Okay. Cylinder also goes on to forever because the line goes forever. So R1 cross S1 is a real space, the infinite cylinder. And at every point along some line going on the surface of the cylinder that doesn't ever cross, then at every point on that, you could find a circle. Okay. So this is much more what it really looks like. You've got a infinite cylinder and an infinite line. And I'm going to add a little bit of language here, which is that corresponds to fiber builders, bundles, and that's what we're actually going to be talking about. So in the language of bundles, you pick two parts of it. One is called the base and the other is called the fiber. And you describe the two parts as a fiber bundle. So this is what it looks like.
Looks like you've compactified one dimension.
What do you mean?
I'm kind of being a little non-serious about it, but it brought to mind the way in string theory, some dimensions get compactified. So at each point you get a Colubion
No,
structure.
this is just a cylinder. It's a
No, I understand that
continuous cylinder.
completely. I understand that completely.
Okay, so what's
I'm just making an
compactified?
analogy, but well, I'm just making an analogy between that and the what you have to do with the 11 dimensions of string theory. At each point, you have to compactify the other dimensions.
Yes, you do in string theory. This is not about string theory. This is
I
about
know. I
mathematics,
was
and
just.
there's no compactification
I
whatsoever.
understand that. I understand that completely. I
Okay,
was just
good.
making a trivial point.
Okay, sorry. All right. So so this will actually be a bundle, and you can choose one to be the base. And usually R1 is chosen to be the base, and S1 is chosen to be the fiber. So oh, I'm sorry. Yeah, that's so the line. So this is a bundle B, and it's equal to the Cartesian product of a line with S1, an infinite circle. Now you can do another kind, which is instead of using the entire line, you can just use an interval. And you would usually use a closed interval like 0, 1 across the circle, and that will give you a finite cylinder. Okay. So those are two types of uh, fiber bundles. And as I said, the main thing, is one has got to be a base, and it's usually R1, and the fiber is usually S1. And the, but these are all trivial fiber bundles. You can get that by looking at the way, if this was an interval instead of R1, you could have it go from -4 to 4, and this would be a finite cylinder, wouldn't be dashed, it would be real. And this wouldn't be dashed because it would be real. And so the interval would be from -4 to 4. So if you looked at the way the surface of this finite cylinder, you could look at arrows going across the surface. And if you had them orthogonal to S1, to the circle, they would just go around forever. However, you can add a twist to those arrows. And if you do them, this is what I was working on before we started talking. You would find that if you went around one time, if you did the twist properly to those angles, initially it was pointing outward. When you came around, it would be pointing inward. Then if you went around again, you'd go back to the original one. So the surface of the first set of arrows that I talked about would simply be an annulus. But in the second one, it would be a Mobius strip. And the one where the twists are added would be a non-trivial fiber bundle. That was the example I was trying to work up before we started the class, but I couldn't get it done. So this is a trivial fiber bundle, but if you add a twist at every point on the edge of every circle, then you can change this into a non-trivial fiber bundle, because this becomes not an annulus, but a Mobius strip. I'm saying stuff that I don't have any pictures for. So is this even at all comprehensible?
Yeah, but
Yes.
you couldn't actually draw that, could you? Because you can draw a Mobius strip, but this one, every one of those loops, how do they stay continuous
Well, the
vertically?
problem is that, if you have an annulus around this circle,
Right.
then it would
Stay on the
have a
outside.
certain amount of size on this side and a certain amount of size on that side.
Right.
The problem is showing the twist, because it would still look like a annulus if you looked at it, head down from here, um, because the arrows all fit in the same place, but they change as they go along. So you would have to show it by having an arrow, and from the center of the annulus going outward, and you would just show it in the first one the same everywhere you go around. But in the second one, you'd have to see it as a picture, and you'd have to see the arrows
Pointing in.
initially going outward and eventually coming back inward, and then continually going around again and eventually going outward where they were when they started. So you'd have to see it as a picture, as a film, with the arrow shown how it twists as you go around the annulus, in order to show it as a Mobius strip. Was that at all clear?
Well, in order to show the twist, wouldn't different parts of the annulus have to have different R1 coordinates? Or else how would
Oh
the
yeah,
twist?
I mean, in the Mobius strip, it's one surface. In the other one, it's two surfaces. Even though it's infinitely thin, the surface of the annulus, there's a one side and the other side. In the Mobius strip, there's only one surface.
Are you using trivial versus non-trivial in an informal sense?
Yes,
Or-
I am, and we'll get to that
Okay.
when we get to bundles. I just wanted to get since it's an idea that most people don't think about very much. This is So the arrows I'm talking about here are tangent spaces, and if you have a non-trivial bundle, then you've got twists in the tangent space that you don't have in a trivial fiber bundle. In a non-trivial one, they have various twists. So if you have in particular, if you're thinking about a connection, then you're attaching to every point on the surface there a tangent space, and that would be a line if you're doing it horizontally here. And so the collection of all of those is a manifold, like I said, an annulus. And if you've got a twist in that surface, then you can have a Mobius strip attached to every point in there. So again, you got an annulus here, you got an annulus infinitesimally close, etc. So um, the 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 fact that it's one-sided as opposed to two-sided is what makes it non-trivial as opposed to trivial. Any of that make any sense to anybody?
A little
Yes, it
bit, but
does.
you can't draw this, right?
Well, like I said, you could draw an annulus and you,
No, but I'm saying because you couldn't make a drawing like this because each of those Mobius strips is two-dimensional, and you can't
is one-sided.
is one-sided, but the one below it, or as you move up and down R1, each one of them are different, right? Or are they all the same?
Well, in this very simple example that I'm doing, they would all be the same. They would just be infinitesimally shifted below.
Each one would be okay. Each one would be a Mobius strip would have two loops around it, being one-sided, however you want to define that. But it would. Okay, I got to think about that one. But it's interesting. I like it.
Yeah. Anyway, so like I said, whenever I saw GR, it's always talked in terms of a connection. But connections are all trivial bundles as opposed to non-trivial bundles. And so I wanted to try and get an idea of how you get the idea from a connection, but it's a subset of all the bundles. Because you can have other kinds of surfaces on there than you do in a usual connection. Okay. Hopefully that was all just, like I said, this was just a really rough idea of how this all works. So because most of the time, like I say, although bundles are mathematically accurate, most of the time, most people don't talk in terms of bundles. Okay. So any final questions?
Can I ask something? Could you go back to that picture of the yellow cylinder? I'm thinking of the annulus, yeah, on the top. If you think of it as a non-trivial bundle, then we were thinking of sort of like a vector pointing in and then pointing out. There'd be something different about the second rotation as compared to the first rotation.
Right, you'd have an annulus around this one, so it would be a little out this side and a little
Yeah.
inside. And if you were doing a trivial bundle, you just have the arrow pointing in one direction, the same
Right.
direction everywhere, orthogonal to the circle. But if you have the Mobius strip,
Non-trivial, yeah.
then you have to have the
It would
arrow
change.
changing its direction.
Right.
First it starts out,
Yeah.
then eventually when you come around
Yeah.
here, it's going in, and then when
Right.
you go around again, it's back out.
Right, but as you go around, the arrow would
Has to
change
change direction as it's
continuously.
going.
It would
Right.
change continuously.
Right.
Is it
Absolutely. Of
possible
course, I
that
could only do it for a finite number of.
is it possible that it changes non-continuously? That as you go around the first time, it's pointed in one direction. The second time, it's pointed in the other direction, but it never changes. You don't see it changing. It pops. It passes one point and suddenly it's
Well,
pointing in.
you could do that topologically, but you can't do that
Right.
in differential manifolds. So that wouldn't work in differentiable manifolds. Everything has to be continuous. And in fact, it's going to be differentiable and usually infinitely differentiable, but that's for much further into the course.
Can I interpret infinitely differentiable as being smooth?
Well, smooth usually means as many differentiations as you need. It's not a infinite. I mean, an infinite differentiable manifold is always smooth, but the word smooth as it's used in physics means as many differentiations as you need. So you might only need 3. So it's the language as it's used, and it's not very precise, but that's the way it's used usually. Smooth means as many levels of differentiation as you need, and C infinity
Differentiate
means
infinite.
actually infinitely differentiable.
Okay.
Yeah. So I hope I'm not being overly, whatever the word is. Okay.
Bob,
Yeah,
are you going to make these slides available throughout the course?
sure.
It would be nice if you'd put them
I can set this set this up as a PDF
Yeah.
and let people take a look at them.
and
Would be
they'd be in
great.
one place, that you'd put them someplace where you could just log in and look at each lecture.
Well, I don't know if I have enough Dropbox space to cover the entire class, but
They're just slides. They're not movies, you know.
yeah, I know, but I would have them as a PDF, and depending upon, I've got a finite amount of space in Dropbox, and so if you want to grab them, I'd say, you could usually have them present for about uh, a month or 2 months, and then at some point I'm gonna run out of space, and I'm gonna have to start moving them to a different disk that you can't get access to.
Okay.
So, okay, any other questions? All
Thanks.
right, then that's what I needed to do. Now I can see where the pause recording is. God, they keep moving things around, drives me crazy.